Alright, so at this point, what we want to look at is inverse trig functions. Again, this is something we looked at to some extent in pre-calc honors. We do want to look at a couple of the ones that we didn't look at before. But let's just real quickly start with finding the inverse function of sine. Okay? Now, the inverse function of sine, in order for a function to have an inverse, it must be what? Must be 1 to 1. Now sine is periodic, so obviously it's not 1 to 1. So what we had done in the past is we limited the domain so it only included a portion that was 1 to 1. But we wanted to make sure it still included the entire range. So what we did is we limited the domain from negative pi over 2 to pi over 2, because that went from the minimum point all the way up to the maximum point, so the entire range was covered. Alright? Once we were able to do that, then the inverse function, f inverse, is the inverse sine. Okay? Inverse sine of x. And what's another name for inverse sine? The arc sine. Very good. The arc sine. The arc sine of x. Now, one of the things I want to make sure we identify here is what is the domain and what is the range for arc sine. Okay, what's the domain, first of all? Yeah, it goes from negative 1 to 1. So you cannot plug anything into the arc sine that is outside of that interval. Okay? So you can't take the arc sine of a negative 3. Alright, you'll get an error because it's outside of our domain. Okay? Now the range... The range of the arc sine would be what? Yeah, negative pi over 2 to pi over 2. Again, as we saw with inverses before, see the domain and the range simply switch. Okay? This is important to understand as you are using your calculator, guys, because as you use your calculator, if you hit inverse sine, it will always give you an answer between negative pi over 2 and pi over 2. So if you want an answer that's in, say, the second or third quadrant, you're going to have to use what? No, you can't tell your calculator to use a different domain.
Minus like 2 pi.
Okay. Minus, subtract from 2 pi, or...
Until it comes back into the interval.
Oh, okay. So you're talking about like coterminal angles. That would be, it's in the same position, but, you know, we take a whole extra rotation around. You could do that. We have coterminal angles. How would I get an angle in the second or third quadrant? Okay, subtract pi from pi over 2.
Rotate it around the y. No.
Wait, what?
Isn't like a rotation.
Oh, don't you like subtract something?
Okay, this is coterminal. Some of you talk about 2 pi or rotating or...
Pi over 2.
Okay. Well, what if I wanted this angle right here.
Which angle?
But my calculator gave me this angle right here.
Just make it negative.
The time 2?
Just add one. Oh, just subtract it from. Subtract it from pi over 2. Depends on.
Not from pi over 2.
2 pi.
From pi.
From pi, okay? Subtract it from pi. These are going to be the same. What are those angles called? We are really rusty on our trig. This is not good.
They're like bro angles.
Bro? start with
非常
what?
我知道。
Reverse.
Rectilinear. No.
Reflective.
Reflective.
Reference angle, okay? Alright, come on guys.
What?
We would have to use reference angles, okay, if we wanted answers in the second or third quadrants or whatnot, okay? Remember when we solved equations, you punched into your calculator, it would give you one answer, but if you wanted the answers from 0 to 2 pi, you would get a second answer using the reference angle, okay? Or if it gave you the fourth quadrant angle and you wanted the answer from 0 to 2 pi, you had to add 2 pi to it to get the coterminal angle. Alright, so we did a lot of that last year. Hopefully that'll come back to memory very quickly. Okay? But you can see
What is coterminal and reference? Which one is which?
coterminal is when you just take an extra spin around, adding 360 or subtracting 360.
That's coterminal.
That's coterminal.
And reference is add to 100.
Well, reference is the angle between the angle you're looking at and the x-axis
Reference.
equals the angle between another angle and the x-axis. So like here we would subtract from 1/8 from pi. Or if we wanted it in the third quadrant, we would add it to pi. Okay? So the reference angle is always an acute angle, but you can use that to find other angles in other quadrants. Okay? Alright, now, because this is an inverse, we actually could sketch this. Okay? So 0, 0 is going to stay 0, 0. But here we have the point pi over 2, 1. That's going to become the point 1 pi over 2. Okay? The point negative pi over 2, negative 1 becomes the point negative 1, negative pi over 2. Okay? And we have that. It's reflected across the line y equals x. Looks a little bit distorted here because they have pi over 2 about equal on the x-axis, about equal to what 1 is on the y-axis, so it's a little squished. But that's the reflection. That's what that would look like, and you could actually see that a little better drawn down here. Okay? So that's our inverse sine. Okay? Now, inverse cosine is essentially the same thing. The difference is that we made we made the 1-to-1 portion by cutting it off from 0 over to pi, like this. Okay? And then we reflect that across the y-axis and you get what you see up there. Okay? So that's the inverse cosine. Tangent. Tangent. You guys know that tangent has vertical asymptotes at negative pi over 2 and pi over 2? So, well, the inverse tangent has horizontal asymptotes at negative pi over 2 and pi over 2. Okay? The domain is all real numbers because for tangent the range was all real numbers. Okay? And then here are 3 that we didn't look at last year, but you can see the similarities here. Okay? We have arc secant, arc cosecant, and arc cotangent. Okay? Because sine... Can we stop the conversation, please? because sine always has to be between -1 and 1, cosecant is always going to be smaller than -1 or bigger than 1. So that's why you see this gap in the middle of the arc cosecant. Same thing here with the arc secant. Okay? Arc cotangent looks a lot like arc tangent. It's just, notice, instead of going from -pi/2 to pi/2 in the range, it goes from 0 to pi. And it's also decreasing instead of increasing. Okay? But there are similarities there with those inverse trig functions. Yeah, Harrison?
Is there, for like arc secant, is there another asymptote at pi/2? Because if not, wouldn't the range just be all real numbers?
There's a horizontal asymptote. There'd be a horizontal asymptote at pi/2. Yeah, see here? It goes from 0 up to pi/2, not including it, and then from the other side of pi/2 up to pi. So yeah, there is a horizontal asymptote here. And that's because for secant, that's 1 over cosine. Cosine equals 0 at pi/2. So the reciprocal of 0 would be undefined. Same thing here with cosecant, has a horizontal asymptote at 0. Okay, so here is basically a table that summarizes all the information that we just saw on the previous screen. It just doesn't have the graphs with them, okay? We have these inverse trig functions, their domains and their ranges, okay? So let's think about our unit circle here, and let's practice evaluating some inverse trig functions, okay? Remember the range, all right? We don't need multiple answers here. These are 1-to-1 because they're inverses, so we'll only get one answer. Okay, so for example, what is the arc sine of -1/2?
Sine of -1/2.
No, the inverse sine of -1/2.
So -2. Oh,
Sine of -2.
You should be giving me an angle, not...
Oh.
Remember, this is an inverse function, so it takes the value and it returns an angle.
Oh. So is it like
Would you? 7 pi/6? That's in the third quadrant. Arc sine is only defined from -pi/2 to pi/2, right?
So then it's
You got the right reference angle though.
So it's
pi/6.
Well, pi/6 would be +1/2.
Negative.
So it's -pi/6. There we go. -pi/6. Alright, so what's the arc cosine of 0? I know it's got to be between what and what? If it's arc cosine.
0 to pi.
0 to pi, okay? The range is 0 to pi. So where is arc cosine equal to 0? Pi/2. Okay? Pi/2. How about arc tangent of radical 3? What's the range for arc tangent?
Negative
-pi/2 to pi/2. So an arc tangent's positive, so I know it's in the first quadrant, not the fourth. So where is the tangent √3?
pi/6.
Pi/3, okay? Remember, tangent sine over cosine. And to get a √3, you'd have √3/2 over 1/2. Well, where is sine √3/2? It's at pi/3. Okay? And then finally, this one you just have to do on your calculator. Alright, this is not a unit circle one, so what do we get here? Making sure you're in radians. 0.305. Okay. And again, that's 0.305 what? Radians. Okay. 0.305 radians. That's an angle measurement. Okay? So remember, inverse functions have these properties, alright? Inverse functions have these properties that f of the f inverse is x. But what about arc sine of pi?
Is that just this?
That's pi, right?
Yeah,
Split.
cancel out.
Okay. This is where it gets a little bit tricky because
No. It is sine.
because in order for it to be an inverse, it's got to be a one-to-one function, right? And we cut off sine to just go from negative pi over 2 to pi over 2.
Zero.
So where sine of pi is 0, what's the arc sine of 0 is 0. Okay? I have to have an answer between 0 or negative pi over 2 and pi over 2. Okay? Alright, so then we have a couple of properties. Okay? Notice for arc sine, if x is between negative 1 and 1 and y is between negative pi over 2 and pi over 2, then sine of the arc sine of x is x and arc sine of y is y. But notice these restrictions because we limited the domain. Okay?
That's what you
Yeah, Terry?
Can we just cancel the sign arc sign away and move the like minus or plus pi to the x until it get into the integral?
You could use reference angles. Sine pi has a reference angle of 0, so to get it into the range, we'd use a reference angle of 0, which makes it 0.
Like the last one.
Yeah, like the last one we just did.
So it is pi, but it is out of the interval, so I minus pi to 0.
Don't think of it as minus pi, because it's not always going to be that. It's going to be what's your reference angle. Okay? If your reference angle is 0, then you go to the first quadrant, reference angle is 0, you're right at 0. Okay? Okay, so let's take a quick look at this here, alright? Here's our original equation. The original equation says that the arc tangent of 2x minus 3 is pi over 4. Okay? Arc tangent of 2x minus 3 is pi over 4. How would we solve this?
Square root of 2.
The square root of 2 divided by, so it's 1. So 2x minus 3 equals 1.
Okay, so you guys, you're using the inverse here, which is tangent. So you're taking the tangent of both sides. Let me write this on a new line. Okay? So the tangent of the arc tangent of 2x minus 3 is going to equal the tangent of pi over 4. Okay? Now here we are assuming that 2x minus 3 is between what and what?
Negative pi over 2 pi.
Yeah, we're assuming it's between negative pi over 2 and pi over 2. Okay? So here, Those will cancel each other out. 2x minus 3 equals what?
1.
1. Okay?
And x equals.
Wait a sec, hang on. 2x minus 3 isn't there. 2x minus 3 for tangent.
I think it have
Yeah, this can be any real number. And get rid of that.
不知道，可能这个比较有没有确认了。
Okay? And that's again because the domain of arctangent is all real numbers. So now we just add 3 divided by 2 and x equals 2. Okay? But that's how we would do it. Now, you do need to think about, hey, what is the domain of arctangent? What's the domain if it was an arc sine? What's the domain of arc sine? Well, it's got to be between -1 and 1. Okay?
I thought domain of arc sine is -2, negative pi over 2 to pi over 2.
That's the range of arc sine.
Oh, right.
Yeah. Okay? Here we have some others. Y is the arc sine of x. Here's y. Okay? Here's x. The hypotenuse is 1. So yes, sine of y equals x over 1, or just x. So that's how we get y is the arc sine of x. Okay? Now this says find the cosine of y. Okay? Find the cosine of y. Well, let's look at this. What's cosine of what would cosine of y equal?
Square root of 1 minus x squared.
Okay? Square root of 1 minus x squared, adjacent over the hypotenuse. Okay? Yeah.
Oh wow.
Okay.
Doesn't follow that domain.
Now, we can go further. Okay? We could go further. If y is the arc sine of x, y would also, we could say, is the arc cosine of square root of 1 minus x squared. Okay? They didn't ask for what y was specifically, they just asked for cosine. Okay? But notice here, we could also take this. If y is the arc sine of x, then what does x equal?
Equals the cosine of y. No, that's not
The y
true.
over
The sine of y.
X equals
Sine of y.
the sine of y. Alright? So, let's think about this here. Okay? Let's see if we can't come up with something a little better. So cosine of y is going to be the square root of 1 minus sine squared y. Huh. That's square root of cosine squared, which is just cosine. Alright, so you see how this kind of all goes together? Alright?
See that one coming?
But to answer the question here, cosine of y is square root of 1 minus x squared. How about for b? We want to find tangent of y. Okay? Arc secant is root 5 over 2.
Why do you have to know that? Like, why can't you just say that the tangent is opposite over adjacent and then do like.
Well, what would the tangent be then?
1/2. Wait, is it y?
Tangent of y.
So it would be 1/2.
It would be 1/2. Okay. Now, let's say we had a different one.
Like, why is it giving me that?
Well, because what if we didn't know? What if we didn't know what the sides were, or what all the sides were? What if we were given one where all we knew was here's y, and let's say we knew this was 10, and let's say that we knew that y equaled the arc cosine of 8/10. Well, what could I figure out then? Which side would be 8? The right side or the bottom side?
Oh, crackers, that's right. I'm going with him.
What is it?
Bottom.
What is it, guys? It'd be the bottom, okay? Because cosine, we now know cosine of y is 8/10, right? So that's adjacent over hypotenuse. Then we could also figure out, if you recognize it as a 3, 4, 5, that this side over here would have to be 6. Okay? So again, that's a way, if you know what the inverse trig function is, and you only know one side of the triangle, you don't even have to figure out what y actually equals. You could then figure out the other sides, and then from there you could figure out whatever trig function you wanted. Alright, so that's just a quick review of our inverse trig functions, a couple little applications, and that's going to get us all ready for actually taking the derivatives of these inverse trig functions starting tomorrow.